Okay, so welcome to week 4, and there's a few things I want to cover today. Just one quick thing on the first exam. I give the analogy because this is critical that you understand the relationship between energy and power, and we use it a lot. The verbal analogy I gave though on the exam was energy is to power as distance is to speed, and the equation, of course, in that case is just that energy equals power times time. Make that all a little bit bigger. Or, another way is energy equals power divided by time. So one way to think about this is that energy is, well, the universe started with a certain amount of energy, and we'll just sort of ignore the dark matter and the dark energy for now. We're still figuring that out. But apparently in the froth of the universe where we live, you can't create or destroy energy, so it's sort of forever. And one way to write that is the change in energy over the change in time always equals 0. So that's kind of the story on energy. Power, though, is the way to think about power is that it's sort of the accountant that keeps track of how energy flows from one form into another. Gravitational into nuclear, nuclear into radiation, radiation into chemical, into electrical, etc. So that's the way I like to think about that question. And by the same notion, we have distance equals velocity times time. So that's the analogy there, or velocity equals distance divided by time. So that's the analogy. Yeah, velocity or speed. Yeah, velocity just as a vector and speed. But they both have units of miles per hour, whereas energy is all.
What if the power equals energy over time?
Oh, did I do it again? Oh, yeah, sorry about that. I said exactly my mistake, and I made it, didn't I?
I'll test it if you
No.
so.
Yeah, thanks. Yeah, that's it, yeah. For some reason, I've got to get my little notebook back, 'cause it comes out of the written hand so much easier than the typewriter, so.
Yeah, for sure.
There's a certain muscle memory with that. Okay, so that's really one of the key things to take away from the first few weeks of 101 or 102. And so let's go ahead and get into the shell. And we're a little bit further ahead this semester than we typically are. We've already taken exam 1. So let's move on. And I think just about everybody has completed summary 1. If not, go ahead and get that in. We've covered the first 3 chapters here. Chapter 1, 2, and 3. So primary energy, solar thermal, solar PV, and then we will move into bioenergy on Thursday. Oh, I also wanted to make note that Kat did a nice job summarizing the due dates, so thanks for doing that. I just posted
Yeah, I printed it out this morning.
Yeah, so I just converted that from weekly basis to your actual dates for the semester, so thanks so much for doing that. Appreciate it very much. And thanks for your posts on the forums as well. So we're also going to move into bioenergy. I have assignment 1 posted here just so you can start taking a look at it. It's I will move it down lower as we get closer to that, but there's just a heads up on summary 1, so start taking a look at it. But today, really what I want to cover is Shramsky. So this paper came out a couple of years ago. It's not something that I discovered on my own, but I have a lot of colleagues who've lived in Missoula, lived in Montana, now live across the country, and are sort of just interested in this big picture view of sustainability. And I guess in the same sense that you might study microeconomics versus macroeconomics. The 102 and the 101 lectures, I mean, they're mainly big picture. I mean, we take a few dives, we took some dives into the science of PV and solar thermal, but what I'm really hoping with these first couple courses in renewable energy is that you come away, with the big picture. So the title of the paper is fairly boating: Human Domination of the Biosphere. Rapid discharge of the Earth space battery foretells the future of humankind. Okay, so what we did in 101. Remember, we went back to 101, and here's just a few reminder numbers for you. In 101, we said that each human, we use something like 10 megajoules per day metabolically, and we use 200 megajoules per day technologically. Okay, now in both of these cases, what are we converting energy from, and what are we converting it to? Because remember, first law, you can't create or destroy it. So metabolically, you're taking what type of energy and converting it to what? So here's multiple choice. When you eat, are you eating radiation, mechanical energy, electrical energy, or chemical energy? Chemical, yeah. So you're taking chemical and you're converting it into, like, a lot of things. Mechanical, moving your body, some other chemical, when you store fat, protein, etc. A lot of it goes to heat, of course. A little bit's electrical, so nerve signals, processing, etc. So that's what's going on there. Now this technological energy, where is that coming from? When we say that? So remember, it's primary energy.
So it's delivered energy.
Yeah, and what form is it in? Primary energy, the only form of primary energy I know that's purely electrical would be lightning. I mean,
No, I was thinking delivered energy.
Delivered, yeah. Yeah, so, right. In this case, we're going to dig all the way back right to Mother Nature, so to primary. Now,
So that it could be a number of things.
it's kind of all the above. Yeah, a lot of it's chemical. That's, our primary fossil fuels. Some of it's radiation, if we're doing solar PV. Very little of it is solar thermal. Some of it is nuclear. In the case of hydro, I'll just call that mechanical energy, etc. So there are many forms, and that, of course, gets turned into all of the above as well. But the secret, if you will, or the end of the story is that ultimately it all just turns into heat. So that's just where it goes. It's like it's the basement. It's so and eventually to heat. Some of it usable, some not so much. Okay, so that's the big picture. So what these authors say is that the Earth is a chemical battery. Now, it's also a nuclear battery. It's also a thermal battery. There's geothermal. We're gonna discuss that as well. But what they're primarily focused on is just the chemical energy stored in the Earth. So they say trickle charge of solar photosynthesis, billions of tons of living biomass stored in forests, ecosystems, fossil fuels. Just in the last few hundred years, that's that first problem we did in 101, that sort of 3 billion to 300 year ratio. We're going to see more of this in summary 2 with the worldometers.
We ourselves are a product of the Earth.
Absolutely, yeah. We are self-assembling organisms that are product of the Earth. Absolutely.
Self-organizing.
Self-organizing too.
Yeah.
and always defying the second law, as it were, too. So transforming biogeochemical. So why put those three words together? Well, the biology obviously was there, sitting on the Earth. Then it became part of the Earth, the geo, but it's still chemistry. Now it says the rapid discharge of the Earth's stored of organic fuels of the human population, the biosphere. I like this word, biosphere, a lot, and the way I tend to think of it is that you sort of have maybe three separate spheres. One that has no biology or technology. You might just call it inert nature, like the moon being an example. You might also have just the biosphere, so you look around you and like, okay, that tree is part of the biosphere, that bird that just flew through the air is part of it, we are part of it. And then you have the technosphere, and that's just, your technology, your bus, your car, your laptop, etc. And if you were to draw a Venn diagram, obviously there's some overlapping there. I mean, think of, the first descent into the Marianas Trench. You had a human, you had a submarine, and you're probing some part of the world that, well, I guess they found a little bit of life, but some part that had really never seen technology or life before. So when I hear the word biosphere, it's not like a physical place. It's just it just encompasses things that are alive. So the conversion of natural habitats into agricultural fields. This has happened, many times throughout human history. Sometimes in a sustainable way. Sometimes, unfortunately, often not. And I think we're waking up to that and turning that boat around in a lot of ways. The resulting loss of native species. A lot of biologists, E.O. Wilson and Stephen Jay Gould being among them, say that we're undergoing what's essentially the sixth extinction on Earth. You've probably heard that before. Emission of carbon dioxide and the resulting climate and sea level changes. Okay, so that's kind of your greenhouse gas effect writ large. Now, in the use of supplemental nuclear, hydro, wind, and solar energy sources, and I think one thing we will see as we move through this book is there's no perfect energy technology. Nuclear has its waste, hydro has its loss of habitat, wind, you talk about the bird losses, and the extraction of precious metals, neodymium being a downside.
You
Yeah.
might know something about this, but I've actually heard that some wind farms can actually change the wind patterns.
I have heard
over
this.
time.
Yeah, I've heard this. In Germany, they'll look at long-term weather patterns, and that's a good one where, is it a good thing or a bad thing? Yeah.
Wind,
Yeah.
But then you have to take into account the comparative nature of what heat generation does to the wind patterns as well. Like the amount of combustion, it creates a bubble of sorts that the natural wind current would divert itself and go around it instead of being able to go through, or would it get
Yeah.
pushed up and over?
Well, yeah, that's a good question. So if you put your wind farm in, obviously you're slowing the wind down, and I don't think there's any case where
Oh, I was just saying,
speed would speed up somewhere else.
With justification of are you going to really say that wind is bad because it's changing the course of the wind streams, and then not look at the similarities caused by the heat, the heat change.
The argument I've heard is that basically like wind, just like water, it just takes the path of least resistance.
Sure.
So if the wind turbines create resistance, then eventually the wind patterns will change and you won't get wind on the turbines anymore.
Interesting.
Over time.
I have not heard
that's
that.
Just what I've heard about particular areas, and it's more like
Yeah.
Southern California, but I just think we could solve that issue by making the turbines mobile.
Yeah, I
So
like the
it's not
mobile
just
turbine.
like a
Yeah.
permanent structure. You
Yeah.
can
Just
do
not
that.
having it so densely.
Yeah, I'm more spread out, yeah.
Yeah, well, and we definitely are moving that direction. We're definitely moving towards a model of distributed power. I mean, yeah, we definitely are. Good call. Yeah, when I was just on the jumbo saddle a couple of years ago, I thought how nice it'd be to have a turbine that was only up while the wind was blowing. You know, something where you had a series of kite. Maybe seen these kinetic sculptures where you might have a kite that sort of pulls the turbine up into the air, and it's doing its thing, and then once the wind has subsided, it just comes back down. Yeah. So
I've heard quite a bit about those kite turbines.
Yeah.
They're just so versatile in their use.
Yeah, yeah. It'd be fun to see a kite turbine or two in the Hellgate Canyon here. And then solar, none of these technologies is perfect, but in my mind, the idea is to put these technologies in places that are otherwise underutilized. New Jersey's done a good job putting solar farms on their old landfills. There's a whole move to do solar on brown fields that aren't really doing much anywhere. Okay, so the laws of thermodynamics governing the trickle charge and rapid discharge. So you can sort of think of like, gosh, the Earth's been on this biogeochemical trickle charge for 1 billion years, and okay, here comes humanity to start the engine, to start the Industrial Revolution. How much fuel was in the tank to begin with, and how long are we going to burn through that? Okay, so the other way I want you to think about this paper is that the Solomon paper was sort of science, and this is a little more technology. It's a bridge between the two. It's a bridge between the two. Okay, there's a couple things in this paper that are a little bit unexpected. It says the Earth is only temporarily poised a quantifiable distance from the thermodynamic equilibrium of outer space. What does that mean? Well, the Earth has not always been alive. You go back and look at the history of the Earth, and one of my favorite quotes is from Neil deGrasse Tyson. Says it used to be a shooting gallery, right? It was just colliding, rocks and just as hot, molten rock is what it was. So it was not alive. The theory then is water came in, other elements came in, and it's just at the right temperature that solids, liquids, and gases sort of coexist at this specific temperature. You go up to the moon. There's no atmosphere there. Now, exactly why that's the case, I don't know for sure. I mean, there's enough gravity to hold a little bit of an atmosphere. It could be that solar wind blows it away. I'm not sure. I do know, however, when I was working at the Department of Energy Office of Space, one of my first jobs was to study the physical characteristics of lunar dust. So the first Bush administration was looking to mine tritium on the moon, and well, you got to get your energy from somewhere, and they were also looking at how the dust itself might foul solar panels or foul heat exchangers. So think about your refrigerator, if it gets that dust on it, or the same thing with solar panels, get that dust. They don't work as well. And then the other idea was to go and make bricks, build things out of the lunar soil. So my job was to physically, catalog the physical characteristics and sort of move towards an engineering solution. Well, Bush was no longer in office. Clinton came in, and the Office of Space where I worked was no longer. But the upshot, or one thing I found most fascinating, was that the astronauts first did take some pressure instruments with them on to the surface. Say, what's the atmospheric pressure? Well, the pressure itself was so small that it was affected by how close they were to the module. Like the module itself was leaking air fast enough that it could sort of be detected by these sensors, but beyond that. So whatever atmosphere is there, we kind of brought with us. So the moon is very close to thermodynamic equilibrium with outer space because it just fluctuates. Whatever temperature is in outer space, that's what temperature it is on the moon. Not so much with the Earth because we have the greenhouse gases that keep the Earth warm.
So that's saying we are a measurable distance from returning to that?
That's what they're saying. They're saying like we're far, and we feel very far and cushy for now. Life's good, But are we driving ourselves closer to that thermodynamic equilibrium? And this is a little,
I see what you're saying.
yeah.
With the radiative forcing of enough of CO2, the elements would effectively overtake a lot of what elements are in the atmosphere.
Well, that's sort of the paradox here, because with, so you might say, well, let's look at Venus. Venus, you might say, gosh, it's very far from thermodynamic equilibrium because it's got that thick, gassy, CO2 and maybe some sulfur in its atmosphere, but not hospitable to life. So the paradox here in this paper is that, hey, we're heating the Earth's atmosphere, which you might think, oh, well, that's a good thing because then, gosh, look at all the things you don't need as much heating. There might be some good things. A lot of people will argue this. Well, sure, what's bad for someone might be good for someone else. But the downside is that if these fossil fuels are gone, and then the Earth starts tipping into its periodic ice age, which we just had one 10, 15,000 years ago, then what do you do? Like, how do you heat the thing back up again when we're heading in? So that's because there have been epochs in the Earth's past. I don't remember exactly when the Earth was just like a giant ice ball. It was just like so frozen that 700 million.
Yeah.
Okay, so that's
Snowballer.
okay. Snowball Earth 700 million. So that's another kind of equilibrium extreme, if you will. Anyway, okay. So so there's several pretty strong statements here. Because there is no substitute or replacement energy for living biomass, I'm not, maybe that's true, maybe it's not. The remaining distance from equilibrium that will be required to support human life is unknown.
Perhaps a replacement for what already is on the planet Earth.
Yeah, so
Is that fact that a lot of energy might radiate out, but not vital energy that the Earth is constituted by.
yeah, I mean, the point is, yes, what you'd like to have happen when radiation hits the Earth, you'd like it to turn into biomass. I mean, that's what every farmer, forester wants to happen. I mean, you want that energy to turn into biomass instead of just bouncing off.
It's conversion there.
Yeah. Okay, so here's just, I like this picture because it's very gettable. When I was first writing that paper in 2008, I was trying to make some very simple analogies. I had the bicycle pedaling and trying to keep up with the car, and I had some dots, but this is just showing that the Earth itself is this chemical battery. I don't know exactly why humankind is like hanging out in outer space, but anyway, the point is that we are draining the chemical battery. There's really no question about that. Every time we break a carbon bond, we are breaking some of this stored organic chemical energy. Now, you might say, gosh, is coal organic? Is oil organic? Is natural gas organic? Well, if you go, once upon a time it was. You go back far enough, those bonds were created by an organism. A lot of times too, just the word organic is just meant to mean carbon and hydrogen. Organic chemistry is usually, yeah.
Same thing could be said about us whether we pay allegiance to the planet that we're constructed from or not. Like, do we
Well,
pledge allegiance to the planet, or
perhaps
are we
there
just rogue entities,
Yeah,
rogue aliens,
aliens among us eroding the
Yeah.
planet, yeah.
denying our existence?
Yeah. I also really like this. So converting diffuse solar energy. So this also harkens back to that Energy 101 paper where we looked at energy densities and said, yeah, just a few millijoules per cubic meter versus the billions, quadrillions of megajoules per cubic meter in fossil fuels. So they're basically picking up these little photons, or the Earth has been picking up these little photons, diffuse low quality, and converting it into high quality, dense chemical. Okay. Okay, in just last few centuries, evolutionary blink of an eye. What's he mean by that? Well, there's pretty common evidence that all humans had a common male ancestor 70,000 years ago. You know, so 10 to the, was it 10 to the fourth, almost 10 to the fifth years. But in well, the scientist I like to study on that is Spencer Wells, and Wells did a project called the Human Genographic Project, and so he would travel to remote parts of the earth where people are sort of from, but nobody goes to, so there's very little genetic diversity, and looked at specific mutations in the Y chromosome and then the mitochondrial, and so there's this so-called mitochondrial Eve, if you will, that all humans have in common. And mitochondrial Eve lived 70,000 years ago, and Y chromosome Adam, if you will. Oh, you know what? I got it backwards. No, because mitochondrial Eve was 200,000, and Y chromosome Adam was 70,000. And the question is, well, why is there a more recent man than woman? Well, it's just men can breed more broadly and quickly and easily. So the common female ancestor is 200,000, and the common male is 70,000. So that's why he says a few centuries, because we're talking hundreds of years versus a couple 100,000 years. That humans were primarily just doing this. You know, we're kind of cooking along on our 10 megajoules a day, and maybe somebody had a horse, and there's a few extra, and maybe someone had some fire, and there's a few extra, but nothing like we have today. Okay. Another thing too, I want to drive this time scale analogy home a little bit further, because it almost always takes less time to destroy something than to build it. So if I'm going to remodel the kitchen, I'm going to be able to wreck that place in like a day, right? Strip it down. But then how long does it take? A month or two to get the thing back. So, and you look at the same thing with other destructive events. How long did it take to build the Twin Towers? A decade or two. They came down in a couple hours. So the destructive acts always take less time than the constructive acts. Always.
Especially if the method has been practiced, how to efficiently destroy.
Sure. Yeah.
Or consume.
Yeah. Okay. So these are the numbers that I really want you to pay attention to, and when you're deciding what equation to include in your 102 paper, and remember every 102 paper has to include an equation, try to work these numbers in. So a couple other numbers that we've looked at before. So if we take that 200 megajoules, so 200 megajoules per person per day, and if we multiply that by 365, we multiply that by 7 billion, we get 500 exajoules. So that's the annual technological energy budget. It's the annual energy technological budget. Global tech. And 200, remember, is just the average human. North Americans are at 1,200. There are other countries, Saudi Arabia and Kuwait, it's like even more, like triple that energy per person. Okay. But what is the zeta? What's a zeta joule? So another way of writing 500 exajoules equals 0.5 zettajoules. And this is also a convenient time to make the distinction between engineering notation and scientific. So typically, and this really motivates the engineering notation where you're typically only going to use a maximum of 3 numbers to the left of the decimal. Once you get past 3, you go up another order of magnitude. So
That's an engineer.
engineering, yeah, engineers always like to think in powers of 1,000. Scientists are fine with just give me a decimal and an exponent. Yeah, and an exponent. But here we are with, and I think this paper. Well, let's just see who wrote this paper. College of Engineering. So there's an engineer, Department of Biology. So there's an engineer and a biologist teaming up on this paper.
A biologist is kind of like an organic engineer in one way or another.
Some biologists have really moved pretty far in engineering, like the whole genome project is a pretty good example of that, yeah. Okay, so, and let's just start with the smallest number we see. We'll ignore this 0 for now. But 2 zettajoules, so tell me what 2 zettajoules is in exajoules. 2,000, yeah. 2 zettajoules equals 2,000 exajoules. All right. So that little blue wave, that's the little blue wave of energy that comes in to planet Earth on, so net primary production in the year 2000. Let's just see if we can find that somewhere else.
So is the 35 representing all of the energy that's available?
The 35?
Yeah.
Um, the 35 is all of the energy that was available 2,000 years ago.
Okay.
Yeah.
And 23, so we've already used up 23.
We've used up 8. We used up 8 in
Oh, I see.
1,900 years.
So we still have 19 is what it's showing?
Yes,
And
yeah.
all the stuff, the other stuff is not usable, so
Yep.
the 500 has recoverable nuclear potential, but that's not, you can't use that.
Well, it's still recoverable. I mean, that represents primarily uranium and thorium. It's still in
Okay,
the
so
Earth.
that does not represent
So
a
much
lot of
more.
those.
There's a lot of thorium.
Just looking at it from a
It doesn't
geological
represent-
perspective.
Yeah.
Fossil fuels, it's just.
Yeah, so what, exactly, so what the authors are trying to do is to break the energy into 2 components, one being chemical and the other one being nuclear.
Okay, so
Yeah.
basically the outset part is the usable, readily available.
Yeah, this is all of the biologically usable, and this is all the nuclear
Okay.
usable, and this is sort of everything else that's there, but it's more expensive to go get. It takes more energy to get it than you grab. It's sort of like, a good analogy would be like, oh, I'm gonna bend over or hike somewhere to get food. Well, if it takes you more energy to move to get the food, then you don't go get it because you lose energy on the way. Yeah.
This is off topic a
Yeah.
little bit, but the thorium,
Yeah.
because Grand Central Station was built completely out of granite, which is fairly high in thorium.
Yeah.
They've actually measured the radiation inside of Grand Central Station, and it exceeds the legal limit for a nuclear plant.
Really?
Yeah, I just
Huh.
read that like 2 weeks ago.
Really? Huh. What year was Grand Central Station completed?
God, you look at
Probably early. I spent some time there.
Not too much of it.
Well, no. Well, we'll see. I don't recommend the bathrooms, by the way. Don't recommend the bathrooms. So, yeah, that's exactly right.
1871.
1871, okay, so 125 years. Well, it's always decaying though, right? The good news is
Yeah,
that
yeah.
there's always less. Every year there's a little less.
Half years, half-lives.
All right, so now, so that's how this breaks down. And the way I like to think of this blue line is this is how much chemical energy is created every year by photosynthesis. That's what that 2 zeta joules is. So, and where is it created? Well, everywhere. You know, the pine trees out on the mountain here will get a little bit bigger. There will be more chemical energy as a result. You know, you're growing in your garden. A lot of it happens in the ocean with algae growth, et cetera. So that's all of it. That 2 zeta joules.
And plants radiate a level of heat as well. Like you said, the pine tree. At the base, you'll see that during snowy times, the snow around the base of the tree will be melted because it effectively generates the heat signature.
Could be, could be. Okay, so they talk about humans leaving Africa approximately 12,000 years ago. Talk about burning wood, then charcoal, then fossil fuels. Saw a lot of this in 101. And then this sort of, you know, so-called ever-increasing rate of energy discharge. And those figures are in the chapter. I've seen that. Okay. So let's just look at this. So it says figure 2 represents the first primary higher quality chemical and nuclear, and their distances from equilibrium. So there we go. Because many deposits of fossil fuels and nuclear ores are dispersed or inaccessible and cannot be currently harvested. That's where that inaccessible comes from. There's also very large, low-quality pools, so soils, oceanic sediments. Kind of used to think that about the gases locked in fracking. I can still remember in the 1970s, some guy just holding up a picture of a rock. Someday we'll be getting energy from this rock. Like, oh wow! But it was not economically or technologically feasible then. It is now. So that's what they mean by that. So, yeah, those gases are lower quality, but you know we are able to go at them in an economically extractable and usable way. But again, if it's too dispersed, you don't bother, or you just can't afford to bother.
Is another name for that syngas, synthetic gas?
No, syngas is usually from the gasification of some other fossil fuel. Thus the syn, you've made something rather than just subtracted from nature. Okay. Okay, so here's the key thing. Therefore, an input, there it is, 2 zeta joules per year of photosynthesis maintains the 19 zeta joules. So you can think of that 19 zeta joules as the remaining principal, and then the 2 zeta joules per year is sort of your annual salary. It's the Earth's annual salary. So the Earth's additional carbon budget is 10% of what it's already got in the bank, and we're consuming, and this is what becomes a little bit confusing about the paper, because you say, oh well, if we only use 500 exajoules of the 2, why isn't it that next year we have whatever 19 plus 1.5 would be 20.5, and if we just used 0.5 again, well then we'd have 22. Like, it would become more and more. Well, these 2 zeta joules of new biomass, they're not being converted into coal, oil, and natural gas. They're just sitting here on the surface of planet Earth. We continue to dig into this principle, Yes.
So your equation could be basically like a calculation, not necessarily an equation?
Yeah, you could do it. You could do a
Okay.
calculation.
So if you did a calculation of like, if humans use twice as much energy, or if humans use half as much energy, how much would they use?
Yeah, you could. You could do a little budgetary equation, but
Okay.
but my only caution there is when if you do your calculation, be sure you identify whatever variables you are.
Yeah.
So, for example, if you just went here, you could say, where, and everyone did a really good job of this, saying where, E is energy, P is power, and T is time. Another thing I want to remind you is that I prefer seeing this in a serifed font. It's just easier to see the variables that way. And also remember, in your paper, you always need to italicize everything. And I would usually just get rid of that. Kind of know what that is. I just do Control I.
Oh, okay.
Control I is
Most
italicized.
of this,
Yeah.
that stuff is pretty obvious.
Yeah, Control I. Yeah.
And usually if you ever need a reminder, you can put your mouse over the little icon on top and then it'll pop up with a little.
Oh, there it is. Yeah, Control I. Yep.
Oh, nice. So
Yeah.
I could just do-
Yeah. So that's just to answer your question there, Mariah. Yeah, just be sure you say what each variable is. Yeah. Okay, so the point is, yes, these 2 zetajoules come in each year. Some of them are just eaten by organisms, right? Some of them are eaten, some of them are combusted, forest fires, et cetera. Yeah.
So I'm just thinking about it, so the 2 zetajoules, you're saying they come in, and in this paper, does it talk about how much we use? Was that in a?
Yeah,
program
it sure does.
diagram?
Yeah, it absolutely
Okay,
does.
So then you could figure out how much are we digging into of biomass zetajoules and how much
Yeah.
of, like stored fossil fuels versus.
That's exactly right, yeah. And when we get into chapter 4 next week, we will look at our current rate of consumption of biomass specifically, yeah.
Yeah, it's a lot like them taking into account how much coal or oil we have left. This is an inexhaustible energy source, so it could proportionately show what potential there is from harnessing solar energy.
Sure. Okay, so here's just some graphs to go along with the numbers. So the question came up before, where does this 35 come from? Well, there it is. And year 0 is just sort of convenient, and I guess I'm sure recorded history goes further back, but this is when people started writing fervently. The other thing to note here is the curvature of that line. Now, so initially we had a negative slope, right? So the slope is negative, and then the slope became more negative, and then the slope became more negative, and it's kind of hard to tell, but you might say, and maybe even more negative. So the rate of consumption is increasing. So we're sitting here at the year 2000. What number is that? Well, I think it corresponds to that 19 that is there. So that's where those numbers are coming from.
Yeah, and the mass industrialization of Asian countries as well, slash and burn.
Yeah, once the economic benefits of an industrial revolution are realized in one country, they tend to be, well, not always, but are sometimes replicated in others.
And
Which,
appetites become quite voracious.
yeah. Okay.
So that's it.
Would you call this it? Yeah, I would call, yeah, I could, well, it's funny. I would call this reverse logarithmic. I would not call this exponential, because an exponential curve never dies. Now, I think Tyler, to answer your question, though, what we're going to see is I think we're going to see this curve turn into a sigmoidal curve, and it might go from this sort of reverse logarithmic into some kind of exponential decay. So we haven't quite reached the dying exponential yet. We're sort of in this inverse logarithmic, or I just kind of made the word inverse logarithmic up because technically an inverse logarithm is an exponential. But if you were to plot a logarithm, and I'll just make a gesture with my hand here. So a logarithm, I'll just make a little drawing on the board. So the log of something looks like that. It's not that easy to see on the internet form, but it has a zero crossing. It goes negative, and it just sort of fades off. It never reaches infinity, whereas your exponential kind of looks just the opposite way, and then your decaying exponential is down here. So I'm looking at this first curve that I drew, and it's more or less a reflection. It's more or less a reflection of the curve that we see here. Is it possible to cross zero? Well, they did it in the latest Mad Max video where there was like one tree left, one dead tree left on Earth or something like that. Not the most uplifting movie. I wouldn't, recommend it on date night, but.
Best picture.
Yeah, I mean, I was sort of like, okay, I get it, but more of an artsy film than a.
It's way sensationalized.
Yeah. Yeah.
I think the reason it did so well is the strong female role.
Strong female role.
Yeah.
Backbone of that.
Yeah.
I still haven't seen it.
So there's some other impressive numbers. By damming rivers and streams and digging wells into the subsurface, humans currently use more than 50% of all accessible fresh water. That's pretty impressive. Most of this water is used for irrigation, so that human activities account for about 26% of the water lost by transevaporation. That's a lot. That like a quarter of all water that evaporates on Earth evaporates through some kind of technology, at a power plant, on an agricultural field. Yeah.
So with the water cycle, though, once that goes back in the atmosphere, doesn't it just, you know what I mean?
Sure, it just comes down. Yeah, I mean, the water molecules themselves are safe. No one's splitting those or breaking them, but they just, the merry-go-round is speeding up, a little faster and faster.
And would you say in a matter of alchemical proportions that we would be a contribution to the water loss in the atmosphere or in the world?
Well, I don't know if we want to say water. I mean, there's a difference between water loss and water redistribution. Because again, unless you're doing electrolysis, that water molecule is still a water molecule. Like, sometimes it's a cloud, sometimes it's a raindrop. Now it's in the lake. Now it's in the ocean. Now it's inside your body. Yeah, yeah.
So I guess the issue is that it can absorb molecules from the air, like smog and like different types of pollutants, right? And then bring it down, like acid rain is an issue.
Yeah. Water will do that. Water will knock.
It's trying to clean the atmosphere, though.
Yes, it will. Yeah, absolutely. We'll knock solid particles, particulates out of the atmosphere and bring them back down. Sure, absolutely. Okay, a couple more things, then we'll take a break. Actually, no, let's just take a break there. There's a few other things I want to look at. It's good stopping point.